Hi everyone. This will be brief, I think. In this video, I want to explain why we leave out solids and liquids in the Kc equilibrium expression, and we'll go over a couple of examples. I first want to describe two types of equilibria: homogeneous and heterogeneous. Equilibria. Homogeneous equilibria is when the reaction has every single compound in the same phase. So for instance, 4NO gas plus 2O2 gas in equilibrium with its product 4NO. Balance this 4NO2 gas. That is homogeneous. Everything is a gas. But if everything was aqueous, it would be homogeneous. Or if everything was liquid, it would be homogeneous. Heterogeneous is if you have mixed phases. And the example I want to use is this one. 2Fe solid plus 3H2O liquid goes to Fe2O3 solid plus 2H2 gas. That would be considered heterogeneous. Those are two types of equilibria. Part B is the crux of the video. When you write the Kc expression, or the equilibrium expression, in Kc, include gas and aqueous. Okay. Gas and aqueous, not solids and liquids. Let's go over a couple examples and I'll explain why we don't include solids and liquids in the equilibrium expression. So for our first reaction, homogeneous, we have Kc. Actually, should we rewrite it? Let's rewrite it. And on an exam, what if you are asked to write the equilibrium expression? What they mean is, what does Kc equal? Following this rule, we include gas and aqueous, not solid and liquid. Everything's a gas. It's products over reactants. You want to test yourself? Go ahead and pause the video and write the equilibrium expression. Then see if it matches mine. Okay. NO2 concentration raised to the 4th power, and its products over reactants. Concentration of NO raised to the 4th, concentration of O2. Interesting. I didn't I didn't reduce this to the lowest whole number. Doesn't matter. Maybe for a particular thermodynamic parameter, like delta H or delta S, the number that they give is for exactly this equation with this stoichiometry. How did that happen, though? Let me... I'll have to look at that. But anyway, yeah, that's right. Anyway, that is the equilibrium expression for this particular reaction. What about for this reaction here, which is heterogeneous? Let me rewrite this one. 2Fe solid plus 3H2O liquid goes to Fe2O3 solid plus 2H2 gas. Let us give a theoretical equilibrium expression where we have products over reactants. So I know that we're going to violate this rule, but I'm going to show you why we have to get rid of the solid and the liquid. Alright, so again, this is not the real answer, but this is the what we would do if we were just following products over reactants. Fe2O3, H2 gas squared, Fe squared, oops, I'm rushing, H2O cubed. Alright, so here's the deal. Fe2O3, this one right here. A concentration of a solid actually doesn't change. The concentration of a solid is mass divided by volume. And as mass goes up, volume goes up as well, proportionally. So this ratio never changes. Is that a big deal? It's a big deal, because if this is a constant, then it doesn't make any sense to put it into an equilibrium expression, because the concentrations of the components that affect the equilibrium have to be changing, or be able to be changed. What we could do is we could fold in this constant into the Kc itself. So again, there is no net change in concentration during the process in solid concentration during reaction. Even if you go down to no solid, it's still technically the same concentration. No net change in solid during reaction, you leave out of the expression. Same thing for the liquid. H2O is liquid, right? So same argument. For liquid. Same argument to leave out anything that's liquid. Alright, so your true Kc, the one that will help you with calculations when we start determining the equilibrium amounts, is this. We gotta leave out that solid here. So the numerator is just H2 squared. We gotta leave out the, ooh la la. I was not expecting that. The water's a liquid and the iron's a solid. So actually the denominator is just 1. Interesting. That is your equilibrium expression for this reaction. Interesting. Part C, and then I'll let you all go. Part C is some more practice. I just want to warn you, I, I kind of hesitate telling you this because it's obvious, but I don't want you to overthink it. Just because something is heterogeneous doesn't mean that you'll have to leave out some compounds, because if the heterogeneous reaction has aqueous plus gas gives you gas, all of those three compounds belong in the equilibrium expression. So being heterogeneous reaction does not automatically determine that one of the components is left out of the equilibrium expression. You can have heterogeneous reactions where every compound is in the expression because every compound is either a gas or an aqueous. Okay, let me show you some, I hope, interesting examples. But I don't know if anything is going to be more interesting than what we just did here, where everything except one component is left out. We have a denominator of 1. Let me try these. I have 2, I think. Zinc, solid, Fe2 plus aqueous goes to, does this look familiar? This is a redox reaction. Reduction oxidation. And I want to know the expression, the Kc or the equilibrium expression. Set it up. The other one that's I think is interesting is this one. O2 gas plus 2H2 gas goes to 2H2O liquid. Alright, go ahead and pause the video and test yourself. Give me the equilibrium expression for those two reactions. Okay, for the first one, it's very interesting because we have only 2 components included in the equilibrium expression, and it's just using the ions. The 2 ions are the ones that are aqueous. What this means is that at the end of the reaction, when it reaches equilibrium, the ratio of zinc ion and iron ion stays constant. You could add more zinc, solid, and nothing will happen because changing the concentration, changing the amount of the solid has no relevance to the Kc. Did I know that already? I probably knew that, I just never verbally said it. What about this Kc? Kc is interesting because all the products are liquid. Your numerator is 1 divided by O2 concentration of H2 squared. Alright, make sure I didn't make any mistakes. I don't think I did. But again, this is its own video because I myself had made many mistakes by accidentally including a solid or a liquid in the equilibrium expression.